Welcome to Spaceverse, your portal to cosmic adventures. Counting future interstellar objects, US 30-meter and Giant Magellan Telescope final reports and decisions, JWST's enigmatic small red galaxies, and their potential role in the growth of supermassive black holes are all topics covered in this episode. The brightest visible planets were out, making it ideal for stargazing. After sunset in the west, Venus and the yellowish Saturn were visible, with Mars rising a few hours later and bright Jupiter in the east. In the northern hemisphere, they could be seen as soon as it got dark without staying up late. Winter officially began on December 21st with the solstice, the longest night, while the southern hemisphere entered summer. Colder winters and seasonal shifts were due to Earth's axial tilt, not its distance from the Sun. In fact, perihelion, Earth's closest point to the Sun, occurred on January 4th. Venus and Saturn drew close over 2 weeks, reaching conjunction on January 18th, just 2 degrees apart. Watching them move night by night, especially through binoculars, was a lovely sight. Looking ahead to Christmas, the International Space Station could be visible if skies are clear. It moves fast and shines brightly, sometimes even mistaken for Santa's sleigh by kids. NASA's website can tell you when and where to look. In Oxford, for example, the ISS passed directly overhead on Christmas Day around 6 a.m., rising in the west and setting in the east. In the northern hemisphere, another meteor shower, the Quadrantids, peaked around January 3, 2024, though meteors were visible from mid-December to January 12th. Up to 200 meteors per hour had been recorded in past years, especially in dark, rural areas. Even 100 per hour meant more than 1 per minute. Light pollution, however, reduced visibility. This shower wasn't ideal for the southern hemisphere, as the meteors appeared to radiate from near the Big Dipper, high in the northern sky. Since they streaked away from that point, it was best not to look directly at it. So my recommendation is to simply bundle up, lay down on the ground or a blanket, something you might use for a summer sun lounger, and gaze directly up at the stars. Fortunately, this meteor shower will not be obscured by the moon, which would otherwise increase skylight pollution. On the evening of January 3rd, the moon will set at a relatively early hour, thus the sky will be lovely and dark. Just after sunset, in the western sky, you'll see the crescent moon paired with Venus, a perfect opportunity for landscape astrophotographers to capture the celestial phenomenon. Plus, on the 4th, assuming the sky is clear, the moon will have gotten closer to Saturn, allowing Europeans to witness an occultation, the actual passage of the moon directly in front of Saturn for the first time. You also won't need to keep yourself up all night long for this. So for those of us in the UK, Saturn goes dark behind the moon around 4:05 and comes back up about 6:30. Nothing to be concerned about if you are not located in that region. What you witness in January 4th is another conjunction, meaning that the distance between Saturn and the moon will be quite small. Return to the subject of observing the moon and Saturn with their rings in close proximity. In this case, you will need binoculars or a telescope for this. Having said that, that is not true right now. The rings of Saturn are vanishing at a rapid pace, making the planet appear to be facing directly towards Earth. Once again, here's just another reason to get out your telescopes. In January 4th, Saturn will align with the moon. In January 14th, a full moon will occult Mars, a celestial event that may be seen across most of northern Africa and North America. Mars, for instance, sets behind the full moon at approximately 7 p.m. local time in Denver, Colorado, and doesn't come out again until around 10 to 8 half an hour later. And just as previously, everyone else on Earth, you won't be able to watch Mars completely go behind the moon, but you will witness the two celestial bodies approach each other in a near conjunction. To find out if you can see both of them, use your binoculars or telescope. Well, let's begin with this stunning image of the Sombrero Galaxy captured by JWST and released by NASA. As far as the Hubble Space Telescope can tell using visible light, the kind that our eyes can detect, it does indeed resemble a sombrero. When seen through JWST's infrared camera, though, the hat's top half seems to disappear, doesn't it? Plus, if you add the rings, it begins to resemble an archery target somewhat. Clearly, it makes no difference which of these two photos is more accurate in terms of color. Simply said, the JWST image isn't a true color picture, it's an artificially colored one. The infrared light it's seeing doesn't truly correspond to any color because our eyes can't perceive it. Areas with shorter wavelengths or greater energy infrared light have been given a bluish hue by the observers, whereas areas with longer wavelengths or lower energy infrared light have been given a redder hue by the telescope. And therefore, it's not the hue that matters, but rather the other distinctions. Reason being that Hubble perceives the visible light emitted by stars, while the MIRI equipment utilized to capture this image, which belonged to JWST, detects the infrared light emitted by blazing dust within the galaxy. Accordingly, starlight is what Hubble detects, while dust light is what JWST studies. When I say dust, what I really mean are the clusters of heavier elements that are found in the space out from stars. Yes, stars consist of incredibly light atoms like hydrogen and helium, but when stars explode, they release heavier elements like carbon, nitrogen, and oxygen in the form of supernovae. In time, these small clusters could coalesce around a star to become a planet. However, some of the visible light is actually blocked by these microscopic dust particles. This is what the Hubble image of the Sombrero Galaxy shows. But the JWST MIRI image also shows the dust distribution throughout the galaxy. So this is the reason the Sombrero Galaxy looks different in the JWST picture without the hat. Simply said, we get our shape solely from the stars. The arrangement of the stars resembles a spherical formation with a flat disk surrounding it, resembling two cooked eggs placed side by side. Alternatively, the dust appears to be located somewhere in the center of the galaxy, after having settled into that flat disk. In 2005, we obtained a very low-resolution image in infrared light with the Spitzer Space Telescope, but it was nevertheless comparable. While JWST revealed the dust structure and, to a lesser extent, its clumpiness, the dust itself almost appeared smooth. The dust is a record of the locations where stars have lived and perished in the past, which is cool because it shows where the heavier elements are produced during stellar deaths and supernova explosions. It contains information on the past of the galaxy. That being said, I do believe that this will soon yield a great deal of scientific information, in addition to being a very beautiful picture. The report from the External Evaluation Panel of the United States Extremely Large Telescope was released as well. The fact that the National Science Foundation (NSF) in the United States was offered, in a sense, an ultimatum to decide between the two next-generation U.S. telescopes, the 25-meter diameter Giant Magellan Telescope (GMT) in Chile and the 30-meter diameter TMT in Hawaii. Congress limited the NSF science budget, so it can only fund one large telescope. You might wonder why two are needed. Why not just build one? The reason is that having one in each hemisphere allows full sky coverage at high resolution, which depends on telescope size. These massive telescopes are engineering marvels and expensive. Report outlined each project's progress and funding needs, $1.6 billion per telescope. Though not a final decision, the NSF will use the report to guide its choice. The European Extremely Large Telescope ELT in Chile, set for first light in 2028, complements the U.S. efforts and is further along. Scientifically, it would make sense to support the 30-meter telescope TMT in Hawaii and drop the Giant Magellan Telescope GMT in Chile, ensuring coverage from both hemispheres. But TMT's site on Mauna Kea, a sacred mountain to native Hawaiians, has led to years of protests and halted construction for nearly a decade. An alternative site in La Palma, Spain has been proposed, though it faces local opposition as well. The report's risk section, which was released, covers all of this. Opportunities for early career researchers, project updates, and governance were also included. Moving on to a more upbeat topic, I came across this research on interstellar objects by Forbes and colleagues. Thus, asteroids and planets are formed in orbit around stars. Interstellar objects are like clumps of rocky material that resemble asteroids. Plus, as they whiz past other celestial bodies, they are literally propelled out of that solar system and left to wander intergalactic space. One of those things may even fly past our solar system if our stars align just so. If you recall from 2017, the first such object was Oumuamua, which originated in a completely different star system. And then there came 2019's Borisov. Two of these interstellar objects have been observed passing past our solar system, and that is all. Astronomers, of course, keep a constant watch on the sky in the hopes of spotting one more as it may soon travel past our solar system. Meanwhile, calculations are being made to determine how many of these things our models truly predict. If a star system were to arise with a plethora of potential rock objects, planets, and asteroids, how many of these would you anticipate being expelled? Because of this, it's difficult to predict how many of these objects there should be in a given volume of space, particularly in cases where multiple stars in a cluster are ejecting rock chunks together in streams, creating planets and asteroids all at once. Therefore, Forbes and colleagues refer to these objects as cousins when they originate from a cluster of star systems rather than siblings when they originate from a single star system. Based on their relative velocities and the direction from which they enter the solar system, we should be able to determine whether two interstellar objects we discover are actually cousins. Oumuamua and Borisov were clearly unrelated, coming from different star systems. Simulations suggest the Sun moves through about 10 million streams of interstellar particles from star clusters. The density of these streams depends on factors like asteroid size, space volume, and how many objects get ejected during star formation. Estimates of how often such objects pass through our solar system vary widely, from 1 per trillion years to 0.1 per year. Still, models predict we could detect 10 to 100 interstellar objects in the coming decades. Studying them may reveal if they share origins. Spotting two in recent years hints they may be more common than once thought. The upcoming Rubin telescope in Chile will likely help us find many more. Finally, I'd like to make a brief mention of two papers, one by Laube and collaborators and the other by Tripodi and collaborators, that were published month about the little red dot galaxies observed by the James Webb Space Telescope. I still haven't gotten around to making a film about these little red bodies, even though they've been all the rage in the astronomy community for the last year. Okay, then we can fix it. Because light takes so long to reach Earth, the discovery of the little red dots was part of a larger effort to locate expanding supermassive black holes in the cosmos, which we perceive as having occurred billions of years ago. In this way, we can learn about the early cosmos and its characteristics. Hydrogen emission, which is often uniformly emitted at a single wavelength, energy level, or color of light, is the signature of an expanding black hole. However, tremendous speeds are experienced by hydrogen if it is around a supermassive black hole, which is progressively absorbing matter and utilizing it to increase its mass. If the supermassive black hole is moving away from you, the light it emits has a longer wavelength, but the light from the hydrogen around it is moving closer to you, so the emission you receive is distorted due to a Doppler shift. These broad lines in a galaxy spectrum are called SMBHs, and they clearly show that the galaxy's center is home to a developing supermassive black hole. And when similar broad lines were sought in JWST galaxy spectra, they were discovered in abundance. However, while examining the photographs of these galaxies, scientists discovered that they all exhibited a striking resemblance to a compact red dot. To find more growing supermassive black holes, astronomers searched JWST images for little red dots, galaxies with photos but no spectra. However, not all showed the broad spectral lines that indicate black hole growth, leaving their true nature uncertain. Are they black holes so bright they outshine their host galaxies? Or compact, star-forming galaxies reddened by dust? Or something entirely new, like isolated black holes without galaxies? Their small size makes it hard to separate starlight from the black hole's glow. Two recent papers tackled this. Tripodi's team studied the black hole itself, whereas Laube's team focused on the hidden galaxy behind its light. Tripodi and colleagues used spectral broad lines to measure the speed of hydrogen and calculate the mass of a black hole 10 million times the Sun's mass, when the universe was just 580 million years old. That's astonishing since radiation pressure from glowing hydrogen limits how fast black holes can grow the Eddington limit. Growing this massive so early suggests either black holes formed through direct gas cloud collapse, skipping stars and supernovae, or they can grow faster than we thought. It is thrilling that these little red dots are reshaping our understanding of the early cosmos and casting doubt on many of our assumptions and models. However, what about the galaxies within these little red dots, which were the subject of Laube and colleagues' attention? One of the brightest little red dots was found closer to Earth, containing a black hole a billion times the Sun's mass, seen as it was 1.3 billion years after the Big Bang. Labbé and colleagues managed to separate the galaxy's light from that of the black hole surroundings. They detected a bomber break, a sharp drop in UV light, indicating older stars. By modeling the JWST spectrum with both black hole and stellar light, they found the best fit was a galaxy 80 billion solar masses in size, with stars around 500 million years old. It is likely located in one of the densest star systems known to science, indicating that it is extremely compact. The characteristics of galaxies at this stage of the universe's evolution can be inferred from that. Despite the extremely strong light from the material surrounding the supermassive black hole, scientists now know that one of these little red dots is actually connected to a galaxy. We need to repeat this process with many more little reds to check if it holds true for all of them or if something else is going on. Naturally, we must ascertain the nature of the early universe's supermassive black hole growth. If you enjoyed this deep dive into the cosmos, don't forget to like, subscribe, and hit the bell so you never miss an update on the latest space news. Keep exploring, and we'll see you next time on Spaceverse. Clear skies, everyone.